But we can see almost the same with different kind of spectroscopy. In this case, I want to show you briefly again what happens with X-ray spectroscopy. This particular kind of measure have risen a very harsh debate in scientific community, because this measurement here were published on very respectable journals such as PNAS or so. What happened in this particular kind of spectroscopy? It was observed that the spectra, observing the spectra, the researchers saw that there are, again, two fluctuating structures in water, which spectroscopically would indicate a model of water in terms of high density and low density water. So again, changing the probe, changing the kind of spectroscopy, we have, again, the evidence of the existence of two different kinds of water. I don't want to go into detail of this kind of spectroscopy, but I can say you that if you like, I can provide you the title and the name and so on, and the reference of this paper. But what I can say to you that they saw exactly what is possible to see with infrared spectroscopy, that is that these two populations depends again on temperature in a quite similar way, and again they depend on the amount of solute. So we have another information. The conclusion of the paper was that through the combination of small angle X-ray scattering and X-ray spectroscopy, we have a picture of ambient water, that is important, it's normal state water, as a fluctuating liquid with a bimodal distribution of local structure in terms of spatially aggregated, strongly tetrahedral patches of H-bond distorted structure. So they say there is something inside water. Probably this is due to the H-bond, but it's absolutely clear that we have two different separate structures. Just a parenthesis, why not three population? Again, this depends by the probe we have chosen. In case of X-ray spectroscopy, we have a much higher energy of the probe, so we have an interaction time that is lower. And in the time of the process takes place on optosecond, that is 10 to minus 18. So this fixes a lower limit to the lifetime of the state. So we know that these two states have a lifetime that is higher than 10 to minus 18. It is in the order of 10 to minus 15. This is what we can get from spectroscopy. We have another kind of spectroscopy. This is an optical Kerr effect. But the conclusion is the title of the paper that was published on Nature 3 years ago. Yes, 3 years ago. It is the evidence of two distinct local structure of water from ambient to supercooled conditions. Again, we have two different kinds of water. The scientists concluded that the two local configurations of liquid water coexist in the entire temperature interval considered, above and below the melting temperature. So it's not something related to the particular condition, to the confinement in very narrow pores, or something like a transition to a bidimensional state. This is a property of water in a very broad range of temperature. We say in all the range of existence of water. Again, they concluded that the lifetime of these low domain, low density spaces must increase with decreasing the temperature. So there is again a proportionality with the temperature. This is the last one. I don't want to bother you more, but this is the last spectroscopy I want to quote. It is terahertz time domain spectroscopy. It's a very interesting kind of spectroscopy because it's based on the femtosecond laser, which trigger an optoelectronic device which produces a bright infrared pulse of radiation. With this kind of radiation, you can probe your sample and obtain information about the electrical conductivity, the electrical properties of the sample. So we can investigate the complex dielectric constants of water. And what happens in this case? The electric constant is usually described by the Debye model. But if we try to apply the Debye model to the experimental results of water coming from this theory, the model doesn't fit. Why not? Because we need a double Debye model that is made up by two parts. We have in the Debye model, we describe the oscillation of molecules and their reaction time. The reaction time in case of water we have two different reaction times. They are very different one is 10 picoseconds and the other one is more than 100 femtoseconds. What does it mean? If we want to try to calculate the relaxing time of a free rotator, if we imagine that water is made up of single molecule, H2O, freely moving in the space, rotating, and in such a case, we should expect a relaxation time in the order of 100 femtoseconds. But we find something more. We find that there are other structures which has a relaxing time that is 100 times higher. So we may conclude that there are aggregates made up of 100 molecules, which is the basic idea to explain all these experimental results. The basic idea is that the ground state of an ensemble of molecules condensed in a coherent state differ from the ground state of an isolated molecules. This seems quite a basic observation, so it's obvious, but it's not obvious because it's not the way how we describe usually the condensed matter. Why we came to such a claim? The description, when we want to describe the condensed matter, we have to couple the description of the matter, particles interacting among themselves, and the interaction of particles with an electromagnetic field. But I'm not talking of an electromagnetic field which has been switched on by the experimentalist. I'm talking about an electromagnetic field which is ever present in a universe. Always the vacuum intended as Aristotle did doesn't exist anymore. The vacuum is a space without matter, but it's not vacuum. The vacuum is filled with an electromagnetic field. So when we want to describe the condensed state of matter, we have to keep into account this electromagnetic field. In such a case, if we, in technical terms, if we want to describe the dynamic evolution of the system, we have to couple the Schrödinger equation with the Maxwell equation. And we have to solve these systems. The solution of these systems produce the existence of long-range forces which account for the structure of the condensed states. Electrostatic forces exist, of course, but they came into the play only after the matter has been condensed by these long-range forces. So the complete description of condensed matter in terms of quantum dynamics foreseen the coupling between particles and electromagnetic fields. In such a case, we observe the rise of the appearance of a ground state whose energy is lower than the energy of the ground states calculated, avoiding the coupling with the electromagnetic field. So this is the real ground states of condensed matter. Come back to water. At this point, we can imagine, but this is just a pictorial representation, of course, that water is made up of different structure. There are free molecules, swimming in space, and there are molecules which are arranged inside confined part of space. In the following, we will call this part of water condensed in coherence domain, because it's possible to show that molecules which share this part of the space share also their phase. They are described by a unique wave function, so they share frequency and phase. In this sense, they can be termed as coherent. Which are these coherence maze? So why we are so interested in this description? Because this interaction induce long-range forces which are responsible for the existence of the condensed states. Short-range static attraction come into play only after the molecules have been brought sufficiently close together by this attraction. We know from theory that the number of particles collapsed in this collective ground state is fixed by temperature, and the number of particles belonging to this condensed part of the matter and the non-condensed part is fixed by temperature by this simple law. But why we want to leave the whole tetrahedral H-bonded molecule? Why we say it doesn't fit? Because if we try to calculate the electronic ground state of water molecule, we saw that it has a structure, the electron cloud has a shape similar to this one. Again, this is not the result of a calculation. This is a pictorial representation. It's just a draw. It is something like this. It's quite smooth. But if we want to justify the existence of H-bond, we should have something like more charges on particular direction. So we want to justify what the chemists call the lone pair. Here there is nothing that which can remember a lone pair. Moreover, hydrogen bonds are described in terms of electrostatic attraction. But if we want to see what happened with the new model, with this more complete model, remember, molecules in condensed state are in a ground state which differs from the ground state of the isolated molecule. At T equals 0, coherent state is a superposition of the ground state and the excited state, namely molecules which that are already collapsed and molecules which are free. Free, I mean monomers or dimers. The electron cloud radius of the coherent states is bigger than the electron cloud's radius states, and it's not homogeneous. In fact, if we want to do the calculation, if we make the calculation, we found that there appears two directions where there is a condensation of charges somehow. There are two maximum angled at 109 degrees. It is more or less a number which fits the description of the H bond. At this direction, together with the OH direction intramolecular, oxygen with the two hydrogens, forms a tetrahedral axis which can account for the hexagonal configuration. So, the conclusion is the theory of coherence domain in liquid does not rule out the tetrahedral H-bonded molecules model, but provides a dynamical framework of that model. So what we are doing here is just to substitute a model with a theory. It is a different thing. At this point, it would be senseless to try to explain the behavior of water outside the framework provided by this model. This is, we try to describe a solution. Sorry, how much time? How much time? Where is the chairman? 10 minutes, okay. Now, let's describe the forces between two non-polar bodies separated by a medium. The description is provided in the framework of the van der Waals general theory of interaction. And we see if we have two molecules non-polar inside a medium, the forces is given by this equation here. Oops, again. This equation. This equation is a very complicated function of the electric constant of the two particles and the medium in between. This is very important. We are not used to this formula that is the most general formula of the van der Waals. We are used to this formula that is the classical London formula. It is exactly the same, but in this case we have done a simplification because we assume that the two particles are interacting in vacuum. In this case, vacuum, this approximation allows us to simplify the formula. But coming back to the general formulation. If we come back to the general formulation, we can see that attraction or interaction, attraction or repulsion between molecules depends on the medium which fills the gap. At this point, we can see that we can have different situations depending on the electric constant of the interposition medium. But in case of water, which is this? We are talking about two different structure medium. So we have a dielectric constant, which is an average between the dielectric constant of the coherent spectrum, the coherent part of water, and the non-coherent part of water. And they have a very, very different values, because I show you that in case of a coherence domain, they are very broad. The electronic clouds is very broad, and it's easily deformable by, the polarization is due to deformation of these clouds of electrons. In case of an isolated molecule, the polarizability is only due to the alignment of with the external field. So we can have very different values. We can see that this is the experimental value of the electric constant. This is the calculated value for non-interacting dipoles, and this is the calculated value for coherence domain. So very big difference. At this point, if we want to put these values in the formula, we see that we have this is the energy, and we see that the energy of the interaction goes as an inverse power of the electric constant. This allows to explain the formation of the nanoaggregates. Aqueous solution used by Professor Konovalov have a typical absorption line in a spectrum which are in the range of 200, 300 nanometer. Hence, whenever the distance among particles exceeds such a length, we can use this formula here, and we can see that energy is decreased by the formation of aggregates of coherent water having a higher static dielectric constant. So the formation of the aggregate is due to the van der Waals forces, but the amount, the stability of such aggregate is due to the fact that water has a two-phase structure, and one of the two phases has a very much higher dielectric constant. Again, this is just a picture, just a draw, to show that whenever the distance is less than a threshold, depending on the substance, the coherence domains are forced to aggregate in order to decrease the energy of the whole system. So whenever the dilutions, say in other words, whenever the dilution exceeds the threshold, nanostructures appear. The feature of the nanoaggregates, we can observe they are stable nano-objects, have a size of 100 of nanometers, which is in the same range of the wavelengths of the characteristic spectrum of solute. Professor Konovalov told us that he see the appearance of nanostructures only in 75% of the solution he tested. This probably is due to this particular threshold, which depends on the spectrum absorption of the substance. So in this way, it's possible to foresee which kind of solute will give rise to the appearance of nano-object. And one more, stable water cluster have a permanent electric charge. In fact, it is possible to measure a zeta potential in nanoaggregates, which depends on the fact that I show you that the coherence domain has this extended electronic charge clouds. So there is a sort of quasi-free electron at the borders. We can imagine in this way. Now, I don't know if I have enough time to explain, probably very quickly, the formation of the easy layer. What is important is the formation. 1 minute, okay, very quickly. The formation of easy layer, what is important is the dynamic of the formation. Easy layer grow in a very peculiar way, in few minutes, but following diffusion law. The process show a robust square root of time dependence. It's a diffusion process. The diffusion is very, very fast, so it's not compatible with the diffusion of polystyrene beds inside. Something else must diffuse into water, but what? Because another problem is the diffusion is the diffusion coefficient corresponds to the diffusion coefficient of monovalent ions. So what are they? But coming back again to van der Waals forces, we can see, I'm sorry, I have to run. We can see that we want to describe the attraction force on the surface of the Nafion film. We have to refer again to the difference between the electric constant of Nafion and of water. Which kind of water? We have two different parts of water. We can see that we have the experimental measure of the dielectric constant of Nafion, which depends on the degree of hydration of Nafion. At the beginning, Nafion is what Nafion has received from the factory is hydrophobic. It doesn't contain water at all, and it's hydrophobic. The dielectric constant is very small, and the forces are repulsive. But when water starts to fix to the SO3 site in the membrane, the dielectric constant of Nafion starts to grow. It increases. At a certain point, it becomes greater than the electric constant of the non-coherent part of water, and the forces became attractive. So this is my imagination. We can imagine that the dielectric constant, the Nafion act as a phase separator. Only non-coherent molecules are available to form chemical bonds. So non-coherent molecules are attracted into Nafion, enter into the membrane, and form a chemical bond inside the membrane. Coherence domain cannot enter into the membrane. They remain at the border of the surface, and so they form this layer that we know, which excludes solutes. It has a very peculiar characteristic. It has a global negative charge, as I showed you before. This could be just a hint to build a theory on the formation of the Nafion. What is important is that the formation of the easy layer has a dynamic nature. This is very important. In fact, if we rinse for an overnight rinse of the surface of Nafion, we will be able to remove completely the easy layer. Because when all the chemical bonds available inside the structure have been filled, there is no room for any other water molecule, and the process of the formation stops. So the last two, and van der Waals forces provide the formation of the nanoaggregates and the easy layer, but we want to have a quantitative evaluation of those phenomena. This requires the quantum electrodynamic description of water. If we want to put numbers inside, if we want to justify what we see experimentally. So we have seen the experimental results from spectroscopy. We have seen the nanoaggregates in ultra-diluted solution, easy water, but we can even explain polymerization, aquaphotomic, the effect of electromagnetic field. What is important is that liquid water is a two-fluid system whose dynamic formation requires the conceptual framework of quantum electrodynamics. Thank you for your patience.
Okay, we have time for a few questions. Yes?
Yes, the paper was excellent, very succinct. You had a reference to Nature 3 years back. Could you give us a specific reference? Was that in 2013? And was it your group, or was it some other group that was correlated with the study?
You are talking about the Kerr effect?
Yes.
The group was an Italian group in Florence. The first name is Righini, if I'm not wrong. I can give you the reference.
And they were looking at the optical Kerr effects?
Yes.
Here?
Coherent domain, but we have coherent domains. We have many, okay? So can we see in infrared spectrum those coherent domains with different frequencies? Number one, this is my question.
It depends on if you are looking at stretching vibration. The stretching vibration are in the range of 2,800 and 3,200. This is the part of the spectrum in which you can see let's say, the coherence domain, yes. You can observe the decrease or the increase of the amount of the height of the area of the peak, yes, with respect on the environmental condition.
Yes, because I think we saw those in near-infrared range very nicely with the Nafion sample, with the Nafion water. And then, again, I think we should talk about, it's easy for people stick to the traditional way of thinking, to talk about 2 phases of water, but I think they are really 3. And we have to be very heavy on that, because the third is a transition between the 2. And
yes,
it's very important to understand it and to follow it. Okay?
Yes.
Yeah. Thank you very much, really. Thank you.
Are you aware of the fact that Victor Schoberger posited the 2-phase structure of liquid water 100 years ago and introduced it to the hydrology community in Austria?
No?
Yeah, he did it through the study of natural forces in nature, and through simple observation, specifically delineating temperature difference, he was able to observe this effect. And he used it to build the most effective log flume at the time that worked in a completely different way and allowed for the transition of cold water into the flume to take advantage of the much denser, heavier, colder water. I suggest you look at his research.
Okay, thank you.
Thank you so much. Have you an idea about the size of these aggregates? And the second point is, how do you reconciliate the very different nature of the 2 states to the overall macroscopic qualities of water that we see from outside, in terms of density and so on?
Yes, of course. The first question is the size of the aggregates. The size of aggregates has been measured by Professor Konovalov. It's in the order of hundreds of nanometers.
No, the aggregates of the dilutes, but the aggregates of...
the dimension of coherence domain.
The coherence domains, yes.
Yes, it's in the order of hundreds. It's about 500 angstroms.
500 angstroms?
Yes, more or less.
Okay.
Or slightly more at room temperature.
I see.
Sorry? 100 nanometers? 100, okay.
Nanometers. Okay.
Go one more. Yes.
It's not working. Oh, it's working now. So, Antonella, does your theory explain the importance of succussion in extremely diluted solutions in terms of forming of solutes?
I'm not able to say. I can see for sure that the distribution of 2 populations in water depends very strictly from the environment, even from very tiny amount of energy. So in such a way, it provides the way to show that water can store information, but in a way that we are at the moment not able to describe in detail.
Thank you.
Thank you very much.